Now we will study about a new concept in probability, which is in a graduate term. Normally we say it is called continuity of probability. Just like calculus, if there is any function that takes any element from R to R, it is said to be a continuous. Is continuous at a point C. At point C that belongs to real line, we say if it is limit extending to C at that particular point is f of C, the functional value, and it is said to be continuous on entire real line if it is for all points that of C that is belonging to R, it is continuous. Similarly, we have a definition in sequential criterion saying that if f is some function from R to R is continuous on R if and only if for every convergent sequence x of n in R, we can write limit n tending to infinity f of x n is same as f of limit n tending to infinity x of n. We can interchange the limit between the functions. Similarly, in the same context, we somehow have a similar definition for probability. So, we will consider first case where we have a sequence of events that is increasing in the sample space. We have E1, subset of E2, subset of E3, subset will go on till E of n. It will go countably infinite time. So in terms of set diagram, we can draw like this. E of 1 is contained in E of 2, is contained in E of 3. Okay. So we say that for an increasing sequence of these events, E1, E2 up to E of infinite, we say that limit n tending to infinity E of n is nothing but the union of E of n is equal to 1 to infinite. This means that for at least one of the events, at least one EI occurs. This indicates at least one EI occurs. So the theorems is here. Theorem. The theorem says for any increasing sequence of events, for any increasing sequence of events E of n, where n is greater than or equals to 1, we can write limit n tending to infinity probability of E of n is nothing but probability of limit n tending to infinity E of n. So how do we proceed to prove this theorem is we need to disjointify. That is, we want to say, for example, we want to say this, this is my, let's try again. We'll consider a set F1 as E of 1, a set F2 as E of 2 but not in E1, which is this, the red one. This is E of 2 but not in E1. This is nothing but F of 2. This is F of 2. And we can clearly see on this F1 intersection F2 is phi, that is F1 and F2 are disjoint sets. Similarly, we can write F of 3 is equals to, which is lying in E3, I've changed the color, is lying in E3 but not in E2, E1, but not in E2. We can write. So if we take again F3 intersection F2 is null, F3 intersection F1 is again null. So this qualifies for disjoint sets. Okay. So it will continue till infinite. So now we can say that union of all the Fi is same as union of all the Ei. So on the now we can proceed with the derivation, when we can write probability of limit n tending to infinity E of n. This is nothing but probability of union of all the En, where n is varying from 1 to infinity. And this is again nothing but union of all the Fi ranging from Fi 1 to infinity. We are invoking this relation. So now we can apply axiom 3, which says that P of we can sum it over all countably infinite probabilities, P of I. Now this can be represented as limit n tending to infinity I is equals to 1 to n P of Fi. Now this can be represented as, for a finite case, limit n tending to infinity probability that union of all P of Phi I, this is for finite additivity. Now this we have seen that this is same as limit n tending to infinity probability that union of all Es, where I is ranging from 1 to n, and this is nothing but E of n. Hence my limit n tending to infinity P of E of n. So we started from here, ended here, hence we derived probability of limit n tending to infinity E of n is same as limit n tending to infinity probability of E of n. The pre-criteria while derivation is we need to understand that E of n is nothing but union of over all i's and this thing. This is true. This and union of all finite sets. Similarly, we have a similar equation for a decreasing set of events. If we start considering E of 1 is greater than is E2 containing E3, that is E of 1, then E2 is contained in E3, then E3. These are decreasing sets. Countably infinite decreasing sets. In that case, we say that at least if we write this limit n tending to infinity E of n for a decreasing set, we mean that every event Ei occurs. That is intersection of Ei for I ranging from 1 to infinity. Sorry, this will be n. Sorry, let me write. It will be intersection of E of n ranging from 1 to infinite. So with this, we will proceed just like the previous case. Probability of limit n tending to infinity E of n is equals to probability that you have this, invoke this, n is equals to 1 to infinity E of n. Or like for simplicity, we can change the variables. It's not a big issue. So this can be written as 1 minus probability of this complement I is equals to 1 to infinity E of I complement. Now applying De Morgan's law, we can write probability that it is union of all Ei's from I is equals to 1 to infinity. Now this we can write, it will be infinite. Now this we can write as 1 minus P of limit n tending to infinity E of E and C now this entire thing actually can be written as E of IC, which is nothing but 1 minus limit n tending to infinity probability E and C. Now this probability E and C is nothing but 1 minus probability of En. So it is written as 1 minus probability of En, 1 minus 1 plus P of n. This is gets cancelled, so it will be limit n tending to infinity probability of E of n. This will be again repeated in the lecture.